Aren't you all so happy that Chapter 17 is over? Chapter 18 is all about environmental chemistry, not covered on the AP exam. Chapter 19 takes us all the way back to Chapter 5. Actually, a lot of the review questions from this at the end of this section, you'll see, do deal a lot with questions from Chapter 5. So Chapter 5 may be something good to review quickly before we go too far into this. So as you can see, we're talking about thermodynamics again. And let's see here. Let's get a felt tip pen, huh? Let's see, a nice red color. So thermodynamics. Hopefully you remember what thermodynamics is. Hopefully you remember what actually happens in thermodynamics, what the study of thermodynamics is. One of the main things we'll be talking about in this chapter is this term right here, entropy. I don't know why my screen's doing that, but we're also going to talk a little bit about the second law of thermodynamics, and we're going to talk about, this is kind of the meat of this chapter, we're going to talk about the sign of the entropy when you're given a reaction. We should be able to look at a reaction to determine whether the entropy is positive or negative. Okay, two things we've learned now since we've last talked about thermodynamics. One of them is we've talked about how rapidly a reaction occurs when we talked about rate laws, and we made rate laws where rate equals K times the concentration of the reactants raised to a power. That tells us how quickly or how slowly a reaction occurred. And we've been recently talking in chapters 15, 16, and 17 about how far towards completion a reaction goes, which we know is KEQ. Okay, we also learned at the very beginning of the year in chapter 5 about thermodynamics. And there's a few laws, and the first law of thermodynamics was that energy is conserved. Energy cannot be created, energy cannot be destroyed. The amount of energy is the same no matter what. And the way that you can find the change in the energy is, remember, you can take Q, which is the heat, which, remember, if the pressure is constant, then Q is just the enthalpy change, and you add that to the work, and the two of those together make the change in the energy. Okay, now we're going to talk a little bit more about what are called spontaneous processes. A process that occurs without any outside intervention, that when you just put the two things together, is called a spontaneous process. It has a definite direction um, and does not exist in equilibrium. An example of a spontaneous process would be if you drop an egg on the ground, it spontaneously falls and breaks. Another example of that, one that has a definite direction, is when you burn natural gas, which is mostly methane. When you burn methane in air, the CO2 and H2O are produced. The important part is that it has a definite direction, that it does not go backwards to reform the natural gas again. So a spontaneous process. That's most of this chapter is what we're going to be that's what we're going to be talking about. We're going to be able to determine mathematically whether a reaction is going to be spontaneous or not spontaneous. Okay, we're going to talk first of all about the factors. Here within a day or two, we'll be talking about mathematically about how you can determine whether something is spontaneous or not. So from the first law of thermodynamics, we've seen that the internal energy can play a role in spontaneity. But we know that you cannot really unbreak an egg, so that is not spontaneous. So there has to be other factors that do play a role in spontaneity. One of those is the temperature. Okay, for example, when you have water that's at a temperature greater than 0 degrees Celsius, the ice spontaneously converts to water. But we know that at that temperature that the water will certainly not convert back to ice. So temperature certainly plays a factor in how spontaneous or non-spontaneous reactions are. Another one is the enthalpy. As we know, if enthalpy is negative, if delta H is a negative value, reactions tend to occur spontaneously, but do not always. Okay, so if you have a negative delta H, they tend to occur spontaneously, but as you know, temperature plays a factor as well. So the two things that affect spontaneity so far are temperature and enthalpy. Okay. Now, before we get into the next part, we have to kind of talk a little bit about what are called reversible and irreversible processes. Whenever we have everything we've talked about when we're talking about equilibrium, those are reversible processes, because we know that the reactants and the products can interconvert reversibly. They can go forward and go backwards. Okay, but a lot of times you have irreversible processes where as it goes forward, it can only go forward and does not go backwards, just like an example of the natural gas producing CO2 and H2O. Spontaneous reactions do occur spontaneously. That's interesting. Spontaneous reactions occur spontaneously. But that does not mean they occur quickly. For example, iron and oxygen do react when it's moist to form rust. That is a spontaneous process, but it is certainly not a very fast reaction. So thermodynamics tells us about the direction, and it tells us the extent of the reaction, but nothing of the speed. We know nothing of speed. Now, the third thing, so we talked about temperature, we talked about enthalpy. The third factor that is involved in how spontaneous a reaction is the disorder, is how the disorder changes during the process. For example, obviously we've got a cylinder here. This one's filled with a yellow gas. The stopcock is closed, therefore the A is evacuated. There's nothing in there. Once you turn that, then it spontaneously goes from here over to here until they are then even with each other. So no work is being done. There's no change in the temperature, so the change in the energy is zero. And the reverse process is inconceivable, but would also involve no heat or work. But the chance of all of these theoretically moving back over to the side B is very, very small. Okay? But something has to make this spontaneous. Here, we've got all the gas on one side. Here, we've got no gas, and it spontaneously fills both sides. What makes that happen? Well, if we look here, in A, we've got two balls on one side. And then this is closed. Once we open it, there's four different arrangements you could possibly have. You could have the blue one move over to this side, just like this one. You could also have the blue one and the red one both stay on this side. You could have the red one move over to this side, or you could have both of them move over to the left side. Okay? So if we just look at it, and we just guess, we're just assuming, let's just say there's only two molecules. There's a 1/4 chance of both of them being on the left side or both of them being on the right side. There's also a 1/4 chance of this. There's also a 1/4 chance of this. If there were three molecules, then we would have a possibility of 8 different combinations. Okay, or a 1/8 possibility of them all being on one side or the other. If there were a mole of the gas, you would have a 1/2 chance raised to the power of 6.02 times 10 to the 23rd, which is obviously an impossible chance of having them all on both sides. So therefore the gas does spontaneously expand to fill both sides of the flask, and cannot spontaneously go back into the right hand. Okay? So, and the reason is because the most probable arrangements are those in which there's equal number of molecules in each flask in a much more, and this is the key, random or disordered state than previously. Okay? So we know that temperature plays a factor. We know that enthalpy plays a factor. If it's exothermic, it tends to be spontaneous. And this is the third one. A process in which the disorder of the system increases tend to occur spontaneously. Okay, highlight that, put a star next to it. That is the meat of this whole section right here. That when the disorder increases, and we'll talk about what that means, the reaction tends to occur spontaneously. Okay? Now, that whole thing about disorder or randomness, all of that is entropy. Okay? That gas expanded into the container because it increases in disorder. You go from an ordered side of all filled with one gas to the whole container being filled with a gas. Ice melts because it's becoming less ordered. Ice is solid, liquid is less organized. Okay. In all three of these processes mentioned up here, you're going from a more random or a more organized state to a more random state. Water goes from a very organized solid structure to a random distribution of water molecules. KCl goes from a solid state, which is very organized, to an aqueous state. Okay, when things are dissolved in water, they become much more random. When you put that KCl in water, the water itself becomes more organized because it's now surrounded in the K and that chlorine ions. And all of this change in disorder that affects the spontaneous chemical processes is called entropy. Entropy. There we go. I want to cross it out there for you. Okay. Now, a couple things about entropy. Notice first of all, the letter that they use for entropy is a capital S. The more disordered or random a system, the larger the entropy. What that means is that if a reaction becomes more random, which we'll look at here in just a second, write this down, the entropy is positive. Okay, so positive means more random. Okay, so it's becoming more disorganized, more random, whatever you want to call it. If the entropy is negative, it is becoming more, try it in cursive, organized, or less random, however you want to think about it. I don't really care. Okay, so when entropy is positive, it's becoming more disordered or more random. When entropy is negative, it's becoming more organized. Okay, which certainly does happen in reactions. Okay, and just like with enthalpy, the way you can find the change in the entropy is the final entropy minus the initial. A positive value, like I said, a positive value for entropy means the final state is more disordered than the initial state. Okay, so this number for this number to be positive, the final state must be bigger than the initial state, which means the final state is more random than the initial state. Okay, a negative value for the change in the entropy means the final state is more ordered than the initial state. For this number to be negative, this has to be smaller than that number. Okay, so here you go. Here's your meat for the whole section. Here's three different reactions or changes where you've got different solutions. Here you've got water going from a liquid to a gas. Okay, now we have to think, is a gas more ordered or less ordered than a liquid? Certainly a gas has much more ability to move around. It's not stuck in the container. A gas is much more random than a liquid is. So therefore we can say that the final state is more disordered than the initial state. So that means that the entropy change for that is positive. Okay? In this case, if you've got silver chloride dissolved in a solution and the water evaporates, you're going from two ions dissolved in solution that can randomly move around back into a solid state that is complete, that has very little disorder in it. So this is much more organized than this side. So that definitely the entropy change for that would be negative. Okay, now this one you kind of think about a little bit more. Here you've got a solid and you've got some gases. And the solids and the gases combine, and this is actually the Rust reaction, by the way. Those actually combine to form a solid. Now, if we were just to look at this, if we took out the gas, there's not really any change in the entropy because you're going from a solid to a solid. However, because you have a gas on your left-hand side and you've only got a solid on your right-hand side, then you absolutely know that this is much less organized. The oxygen gas is much more organized. So therefore, the product has much more order. So if that is the case, then we know that it has to be negative. You're going from a random state to a non-random state. Here you're going from a more organized state to a more random state. So therefore delta S is positive. Okay, so those are the three things that affect the spontaneity of a reaction. The enthalpy change, the delta H, the temperature in Kelvin, and the entropy change, delta S, in a reaction. Okay, you absolutely have to be able to look at a reaction like these and be able to determine whether the entropy change for that reaction would be positive or negative or possibly zero. Okay, now the change in entropy is related to the heat transferred during the process. Okay, and of course could use some calculus to solve, but not always. We will not be doing the advanced calculus ones. For a process that does occur at constant temperature, the entropy change for the system mathematically can be found by taking the heat exchange, which again is just, that does not mean for the reverse reaction, but it has to be for a reversible reaction. So QREV is the heat transferred in a reversible process. But the entropy change can be found mathematically by taking the heat divided by the temperature in Kelvin. I've never seen them actually had to solve a problem using that, but that is it is on the AP exam, something that they certainly could ask you about. Sorry, this is boring, huh? We haven't got to the good stuff yet. Just wait a couple of days. Okay, since the heat and the temperature are independent of the path taken, S is a state function. Applies to any isothermal process. That means no temperature is lost, not just those that are reversible. So if they ask us to calculate the entropy change when you've got a mole of water converted into a mole of steam, they would give you the heat of the enthalpy change for the reaction, which is this. Divide that by the temperature, which they don't tell you, which we have to, I guess, assume is 100 degrees Celsius. Oh well, 100 degrees Celsius, so 373 Kelvin. And they find that it is joules over Kelvin. Now you'll notice the units here, the units for entropy on the exam will be a form of joules over a temperature, over Kelvin. Where that can be confusing is once we start, we're going to be using equations that involve delta H as well. And in general, our units for delta H are going to be something such as kilojoules or kilojoules per mole. You've got to be really careful in that if the units for delta H are kilojoules and your units for delta S are joules, those don't combine. You either have to convert your kilojoules to joules or take your joules in the entropy and change them to kilojoules. Okay, we haven't gotten to that equation yet, but that is certainly a common error that students make, is they mix up their units like that. Okay, so we know that most reactions have a direction. They are spontaneous in one direction. Usually, oh man, I guess yawning's better than coughing, huh? Not spontaneous in the reverse direction. The reversible reactions can go back and forth. Irreversible reactions can't. The spontaneous nature of a process is related to entropy, the randomness or disorder of a process. And like I said, most of these questions, especially question number 3, go back to chapter number 5. So try those out tonight. We'll talk about them tomorrow in class. Thanks a lot. See you later. Have a nice night. Trying to get this to shut off now. It won't. Come on.